Hello, everyone. I'm Petr Dolezal. I'm a final year PhD student, so looking forward to any of the job interview invitations. And I'm going to speak to you about how can all weather forecasts help us design future systems. And so throughout history, technology mostly served us to isolate us from the outside world. We've got buildings with heating, air conditioning. But as we try to move to a sustainable future, we're going to have a bunch of technologies that will make us more exposed to weather, notably wind turbines, photovoltaics, heat pumps, all things in the electricity sector. So to introduce one such problem where we are at the mercy of weather, let me be a weatherman for a minute. And so this is a satellite view with a wind overlaid on top of it. This is 1.5 years ago in June. And so you can see on this video that there is this big kind of front coming in, pushing what will later become this large cloud, a lot of wind behind. This is now the morning, so these are 3-hour increments. And by the end of the day, you're going to see that this cloud has been pushed all over Germany. And this is now 7 p.m. This is the peak of the demand. Most of Germany is covered by this cloud, so PV production plummets. You can see the wind kind of collide, so there is very little wind as well. So what do? Well, in this day and age, this is when the coal plants come on, but we want to avoid that in the future. So there's options. We can purchase expensive batteries. We can rely on nuclear in Germany, who knows? But there's also all these other places which have energy, right? There, as you can see, the sun is shining on Britain, France. There's lots of wind everywhere. So you can use the network, the transmission network, reinforce it in some way, and look to bring, for this particular situation, power from elsewhere. There's many different options. And so we might want to investigate, for example, if we can bring power from the UK to Germany. But the problem is, this is a situation that happened in the past. This is a situation that happened in the past. How can we be certain that this exact situation is going to happen in the future? It's almost certain never will. Can we rely on UK having power when Germany doesn't have it? And so how do we understand this? So this is the general problem that we don't know the weather of the future. These power systems we're building for the future, how can we rely on them? This is where this work kind of comes in. This is a backbone, like a data-centric backbone of my thesis. And so let me introduce you to the star of the show, the expired ensemble weather forecast. So ECMWF is one of the best forecasters in the world. A lot of the products of Metaphys are just post-processed forecasts of ECMWF. And I'm going to focus on this ensemble forecast. So ensemble forecast is when we run multiple different versions, and then because of the butterfly effect, the chaosphere, the atmosphere, they kind of diverge, and that gives us constraints on the confidence of our forecasts. And sometimes they've been running it beyond the horizon of standard weather forecasting, which is like 2 weeks, all the way till 6 weeks, 7 weeks. So there's the ENS extended. And it's notable that also they use this physical system that they use in the numerical weather prediction to produce ERA 5, which is this kind of nicely interpolated record of all the observations of weather that we've had. And so they're kind of interchangeable data sets. This is extremely popular, ERA 5, in most of science. Now, so why would this is the ENS extended, why would they be useful? So first of all, you can just look at the structure. The beginning, that's what your weather app tells you for the next week. They all agree, all the ensembles are producing same results. We're confident what's going to happen in the next week. At some point, they're going to start diverging. And so you can see that for 4 of them go up above 0, and 1 of them goes below 0. This is a middle is temperature. And from about the week 2 onwards, they kind of produce different versions of the future. You can still extract some ranges from them, but they're mostly independent sources of data by this point. And that's very useful because, okay, imagine we're building that grid. We're trying to reinforce that grid in a specific way. We've got a model that we want to understand how will that help. And that model has weather inputs, right? We need to supply some weather to it. And so you can think of every single weather input at every single location being like an axis that we can slide in. And so if you look at all this space, this is the input space of our model. We can sample from this. We could plug any of these values into our model. It would give us some output. Of course, most of these values are nonsensical, extremely cold places next to extremely hot places. So there is some sort of subspace of this, which is the physical weather situations that can occur. And that's what we want to evaluate the system on, because that's as much as we can predict of the future. We can only predict the future as a probability distribution of some samples that we can kind of draw from or evaluate our systems on. But we only understand what this is based on the weather record, right? The weather record forms a continuous trace through this space of possible weather, and that's how we try to understand the space. But if you kind of if you don't know what the space is, it gives you very sparse view of all the possible weather situations. And here, the ensemble forecasts, which are initiated from the known weather, but then kind of diverge and predict some other plausible weather that could have happened had the atmosphere been slightly different. They map out the rest of the space, and you can see that we got now a much better view of what's all the possible weather that could have happened. And now, so let's ask a specific question of all the data. So let's go back so we can kind of project it down into some sort of axis. So here we asking question was the average 100-meter wind speed difference, so spatial averaged across Germany minus that one in the UK for the situation from the beginning. And so we can look at the weather record from 2017 and all of the data points, and it gives us this histogram. And so we kind of know that it's always a bit windier in the UK, and we get the range. But there's this weird gap where it's not, there's like data missing in the UK. And is it a real feature of the weather system, or is it something that just happened in 2017? Right? This is the kind of question that we don't know. So the sample that I showed you at the beginning, the spaghetti plots, we can see that all the data in that one spaghetti plot is equivalent to almost data from a full year of weather. But of course, this is like a winter sample, so we need to do an average of over the whole year or accumulate them. And so if you look at all of the ensemble forecasts from a whole year, you can see there's so much more data as yet another source that we can use. And you can see that for that particular question, -10 is equally likely as +7. And you understand these distributions much more precisely. Just to kind of drive on, this is a logarithmic histogram. The frequency is on a log scale. So if we look at the tail, where we only have 1 or 2 situations that happened in that year, we've got hundreds or thousands that we can do statistics analysis on in that bigger data set. So as the view, so this is this gives us extremely powerful data set that we can use for many purposes. We can extend the 50 to 80 year long record in up to 15,000 years. We can, for a single event that happened in the past that's kind of rare, we have suddenly a distribution and hundreds and thousands of them. And we also can scale up machine learning techniques that are established, but we just couldn't apply them for weather due to the lack of samples. Some come to mind as optimization with constraints, or nowadays there is new diffusion methods for improving climate model outputs, where you take the kind of low resolution climate output, and then you train this kind of same diffusion is what's behind the big breakthrough in AI generation, where you just kind of generate a weather sample that matches the conditions that the climate model output gives you. And with that, I thank you for your attention. And if you need any more details, I have a website where I document a lot of this progress. So thank you for listening.